Hi, I'm Ben Pierce.
I'm Jeff Anderson. We're with Integral Ecology Group, and we're in the process of establishing an unmanned aerial vehicle, or UAV, remote sensing program.
The goal of our presentation is to introduce the concept of UAV remote sensing for reclamation monitoring.
So we'll introduce some of the sensors, give a brief overview of how they work, and then go into the strengths and weaknesses of each sensor.
After which we will show some examples of how these sensors can be applied for reclamation monitoring, along with some of the strengths and pitfalls of this UAV remote sensing approach.
And finally, we'll provide some thoughts on what to keep in mind when starting your own UAV remote sensing program.
Let's get started. Technology is rapidly progressing in the field of UAVs and in the sensors they can carry. Every year, there are better and more cost-effective options for UAV-mounted sensors, which are able to provide detailed maps of small areas. Along with the advances in technology, these tools have become more user-friendly, particularly as it pertains to the UAV flight and data collection. It is now normal that data collection occurs with the UAV autonomously following a predetermined flight path, developed in relatively easy-to-use software. Data processing ranges from quite easy for simple or cloud-based analysis to extremely difficult for advanced applications. With these advances, UAV-based remote sensing is becoming more accessible and has more possibilities for application in the field of mine reclamation.
The first sensor technology that we will talk about is light detection and ranging, commonly referred to as LiDAR. The easiest way to think about this technology is that it is a laser rangefinder that records distance from a known location thousands of times per second. Using all these readings, a 3D model of an object or landform can be developed.
A lot of folks will be familiar with LiDAR for creation of digital elevation models across a large area, usually mounted on a fixed-wing aircraft or helicopter. Mounted on a UAV, LiDAR can be flown at a much lower altitude and can create a much higher density of readings, referred to as points. Generally, LiDAR from a manned aircraft will create a point cloud with a density of less than 20 points per square meter, where UAV-mounted LiDAR can create a point cloud density of well over 1,000 points per square meter. This high density means that even with relatively dense vegetation, some of these points will slip through the canopy to the ground.
The ability for LiDAR to penetrate through vegetation and get ground readings makes it the ideal technology for monitoring ground movement on vegetated areas or for measuring mature vegetation on reference or reclaimed sites.
The next technology that we will discuss is photogrammetry. This is where photos taken from known angles and locations are stitched together by software to create models and imagery of an area. Recent advances in photogrammetry software have made it cheaper, easier, and faster to use, which has been the main driver of why this process is now so accessible.
Here's an example of a photogrammetry software called EggSoft Metashape. The blue squares, seen here, represent the layout and location of each image taken. The images are then run through a series of steps which result in a 3D model, a digital elevation model, and an orthomosaic. There is a common misconception that photogrammetry is less accurate than LiDAR, which is not necessarily true. photogrammetry can achieve the same accuracy as LiDAR on bare and sparsely vegetated areas, but cannot process shadowed areas beneath dense canopies. For this reason, it is not a good option for monitoring land movement below vegetation. The area shown was flown with both LiDAR and photogrammetry. On the left is the digital elevation model resulting from LiDAR, and on the right is the digital elevation model resulting from photogrammetry. Both sensors are capable of achieving our target accuracy of less than plus or minus 5 centimeters.
Photogrammetry can be conducted using specialized cameras such as RGB, multispectral, or hyperspectral. Most entry-level UAVs come with RGB cameras, which produce a true color image from the combination of red, green, and blue bands. They recreate the vision of human eyes. Multispectral cameras record images for 3 to 10 spectral bands. Not only red, green, and blue, but can also include bands in the near-infrared, thermal, and red edge wavelengths. Hyperspectral is similar, but collects data on hundreds, even thousands, of narrow bands of spectra.
Multispectral sensors can be used to generate vegetation indices, which can in turn be used to generate models for vegetation health, cover, and above-ground biomass. Vegetation indices are based on wavelengths of light that are preferentially reflected or absorbed by plants. Shown here is a diagram of wavelengths that are reflected and absorbed by plants compared to inorganic material. As you can see, in the near-infrared, or NIR region, a significant amount is being reflected by healthy plants, while it is mostly absorbed by inorganic materials. This is the basis for the most common vegetation index, the Normalized Difference Vegetation Index, or NDVI, which is a comparison of light reflected and absorbed in the NIR and red wavelengths. It's worth noting that it can be very easy to make a map showing NDVI or another vegetation index, but there are hundreds or thousands of vegetation indices, each with a very specific use case. All of them require ground sampling to be useful and should only be used with a clear understanding of what is actually being measured. Hyperspectral sensors can be used to generate those same models, but can also be used to generate models to estimate biodiversity, cover of specific species, and even specific water and soil quality factors. Hyperspectral sensors are very expensive, and the data can be difficult and time-consuming to process.
Before we move on to potential applications of these technologies, it's important to point out that any remote sensing operation requires extensive ground truthing. Location, both vertical and horizontal, are ground truthed by placement of ground control points, as seen here. These are small targets visible by the sensors, which have been marked by a survey-grade Global Navigation Satellite System, or GNSS receiver. These points allow for accurate georeferencing of the imagery, as well as compensation for any distortion which may occur in the course of image processing. It's important to note that the accuracy of any imagery that is produced cannot be higher than the accuracy of the location measurements for these ground control points.
The use of UAVs to conduct reclamation monitoring activities offers some clear benefits. First and foremost is a much better understanding of spatial heterogeneity of characteristics across a study area. Instead of using multiple plots to create a mean of plot conditions to represent the site, we can instead use a smaller subset of plots in order to train a model or ground truth a measurement. This differentiation is between a survey to create a mean or a census by which each pixel in an image will have a measurement associated with it. This helps to control error associated with generating a mean, which is a major source of error in traditional reclamation monitoring.
Yeah. Another benefit of using this UAV remote sensing approach is going to be an overall improvement in safety over other methods of monitoring. There's no doubt that a lot of safety departments are going to be concerned about the use of UAVs because it's a relatively new approach. But when operated in areas which have been cleared of personnel and machinery, there's really a very low risk of injury or damage to property. This is going to be especially pronounced when the alternative would be a monitoring program with a higher survey intensity, which is going to include more personnel working hours, as well as working in potentially steep and uneven terrain and working closer to heavy machinery.
Yeah, for sure. The final benefit that we'll raise is cost. Even with ground truthing and equipment rental costs, UAV remote sensing programs are generally much less expensive than traditional reclamation monitoring surveys. For vegetation applications, costs might be slightly higher in the initial monitoring years, as there's a higher number of plots that are necessary in order to build a vegetation model. After those initial years, the number of monitoring plots will be greatly reduced, and with it, cost. So given some of those benefits, let's explore possible applications for UAV remote sensing in reclamation monitoring.
Firstly, looking at the placement of reclamation materials, using LiDAR or photogrammetry, it's possible to create a digital elevation model of bare ground at better than 5 centimeters vertical accuracy, as shown here. This makes UAV remote sensing a great option for cover placement surveys by creating one elevation model before placement and one after. The difference between the two will tell us the exact depth of cover placement across the area. The alternative to determining cover depth would be by digging pits, either manually or with an excavator. Using a UAV for this task is safer and more efficient. Due to delays in cover placement, we have not conducted a post-placement survey on the area shown. But once we do, we will be able to compare before and after elevation profiles and create a highly detailed map of cover placement depth across that area. Going forward, we will be able to monitor any erosion channels that may be developing on the area. We can also use these tools to assess the characteristics of reclamation materials. Here's a trial area at a mine out in Ontario, where a peat mineral mix was applied as a growth medium. However, due to the heterogeneity of the materials, some areas had high levels of organic matter and others had very low. We can see on this 3D model that some areas on the trial are lighter, indicating lower peat content, while some are darker, indicating higher peat content. Using machine learning image classification software, we were able to automatically classify areas into bins of high and low organic matter contents. This information can be used in an ongoing basis as a covariate with indicators of revegetation success.
Moving to monitoring revegetation, there is a huge potential in these tools for monitoring the growth and characteristics of vegetation on reclaimed mine areas. Shown here is a site which has co-located ecosystem flux measurements with traditional measurements of leaf area index, vegetation, and tree mensuration surveys. The permanent sample plots can be seen in white, and the multispectral derived vegetation index can be seen as the green to red heat map in the background. Datasets like this can be used to build correlations between measurements, which lower the reliance on averages between sites.
LiDAR data can be used in mature forested areas for generation of tree mensuration data, which is normally costly and time-consuming to collect. In this dataset, we have automatically detected individual treetops and segmented individual trees using the R package LiDAR. So to finish up here, we just want to share a few quick tips for folks who are considering starting their own remote sensing program.
Yeah, I think the first and the biggest is to have a clear understanding of what you want to be able to achieve with your remote sensing program. Is it going to be mostly to create 3D images of bare, non-vegetated areas? Will it be to monitor vegetation on reclaimed soils, or would you like to do it on reference sites as well? And what kind of area do you want to be able to survey with each flight? Defining the scope of this program is going to help you decide if you need a $1,000 Mavic drone or a $300,000 LiDAR-equipped fixed-wing drone.
Our next piece of advice would be to call in the experts. You're really going to want to shop around for your equipment supplier and your technical support team. Usually your vendor is going to become your first line of tech support, and you're going to be needing to rely on them a lot. We have used a company called Measure, and we really needed to call them morning and night, 7 days a week. So you want to be sure that your program is supported.
Yeah, for sure. And building on that, the final tip is you got to know your limits. It's really easy to get in over your head with a UAV remote sensing program. So you need to choose a flight platform that is suitable to the abilities of your pilots and sensors that have processing needs that fit the amount of post-processing that you're willing to commit to. And remember that everything will need to be ground truthed. So make sure that you have the skills and abilities to collect the needed data in order to do that. And remember that for any vegetation analysis, you're going to need to build models using that data. And so you're going to have a modeling team that is able to take on that task.
Yeah, we really appreciate your time for joining us for this presentation, and we welcome any questions that you have. Thank you.
Thanks very much.